In Notes 15, we learned about a new type of hypothesis test known as an ANOVA test. And what we saw at the end of that section of notes was that if we reach a conclusion, we might reach a conclusion that goes something like there's sufficient evidence to say that there's a difference between at least two of the population means that we're comparing. Now, Note 16 is going to focus on how we can talk about what that difference might be by using confidence intervals. But because we have multiple different groups, we actually need to compare all the groups to one another, which leads us into this topic called simultaneous confidence intervals. And to understand that, we need to do a little bit of background on probability to understand why we're going to have to make a couple of the adjustments that we will need to do. So the first thing I'm going to talk about is this idea of something being random. There's sort of a colloquial way that the term is used to just mean like kind of weird or unexpected or something like that. But in statistics, random has a specific meaning, which is some sort of phenomenon or event with an uncertain outcome. So this could be all sorts of things. It could be if I'm going to shoot a basketball, whether or not I make that shot is random. It's uncertain. We don't know for sure. The weather. I don't know if it's going to rain tomorrow or not. So there's lots of ways that we can use this, and sometimes we know the probability of a random event and sometimes we don't. But another thing that we need to bring up is if we have more than one event. So let's say we have two events. We'll call these events independent if one of them occurring or happening doesn't affect the probability of the other. So there's lots of examples of this. We're going to see an example in just a second. I'll give you a case where two events are not independent. Let's say one event is whether or not it rains, and another event is whether or not I take an umbrella with me when I leave the house. Now, knowing that it rained is going to change the probability of whether I bring an umbrella. So those two events would not be independent. Some events that would be independent is the example that we're going to look at here. So let's say that I'm rolling two dice, and the first roll and the second roll, they're independent of one another. If I roll a 1 on the first die, that has nothing to do with how likely it is that I roll a 2, for example, on the second die. So when two events are independent, if we want to know the probability that both of them will occur, we can actually just multiply the individual probabilities together. So what we're going to start with is we're going to hopefully kind of convince you that this actually works. And we're going to use this example of two dice to do that. So when I roll a single die, there's 6 things that can happen. I could get a 1, 2, 3, 4, 5, or 6. And you can see those 6 things right here. And if I roll a second die, there's 6 things that could happen on that die. And so together, that actually makes for 36 possible outcomes. So you can see my table here. You can ignore the x's for now, but these are the 36 different things that can happen. So let's try this idea of this probability of independent events that I just talked about. What's the probability that I get a 4 on both dice? Well, there's a 1 in 6 chance that the first die is a 4. There's a 1 in 6 chance that the second die is a 4. And so I'll multiply 1/6 times 1/6, and I get 1 over 36. And you can see that this is actually just one of the 36 boxes in my table here. So far, this probability rule is kind of matching up with what we're seeing if we just kind of picked through the outcomes in the table. But that was a pretty simple one. Let's try it a couple more times and see if it keeps working. What's the probability I get an even number on both dice? Well, half of the time I'll get an even number on my first die. Half of the time I'll get an even number on my second die. So if I take the 1/2 times the 1/2, that tells me that a quarter of the time I should get an even number on both dice. And that's what these purple X's here represent. So this is a 2 and a 2, both of those are even. A 4 and a 2, both of those are even. And we end up with 9 of the 36 boxes in this table represent cases where we have 2 even numbers. And so again, what we're going to see is that this is actually the same 1/4 that we calculated using the formula that I mentioned above. So let's do just one more of those to really convince ourselves. what's the probability I get a number that's less than 5 on the first roll? So a 1, 2, 3, or 4. There's a 4 out of 6 chance that that happens. And I get a number that's 5 or greater on the second roll. So that's either a 5 or a 6. There's a 2 out of 6 chance of that. Multiply my probabilities together, I get 2/9 or 8 out of 36. You can see that if I mark off those same places in my table here, there's 8 of those sort of orangish X's, and so this works again. So far, all I'm trying to convince you of is that this idea of multiplying the probabilities of independent events together actually can tell us how likely it is that both of those events will occur at the same time. And so why do we even care about this? The reason is, when we're talking about confidence intervals, you can think of a confidence level as being kind of like a probability. So before I actually gather my sample and make my confidence interval, we've learned that a 95% confidence level means that in the long run, 95% of the time, my confidence intervals will contain the population mean. So if I'm about to make one, the outcome, whether or not my interval will contain the mean, is uncertain. So we can think of that as a random event, and the probability that my interval will contain the population mean is 0.95. So let's say I'm going to make two 95% confidence intervals. The first one has a 0.95 probability that it contains the mean. The second one has a 0.95 probability that it contains the population mean. And if I multiply those together, I actually find out that I'm only about 90% confident that both of my confidence intervals contain the population mean or whatever other parameter I'm looking for. So I'm actually not 95% confident in the two intervals together. I'm only 95% confident in each one individually. And what's going to happen if I add more intervals to this idea? Let's say I calculate 3 95% confidence intervals. Well, I'll do what I did here. I'll do 0.95 times 0.95, and then I'll multiply by another 0.95, and so I'll get 0.95 to the third power. And in this case, I'm actually only about 85 or 86% confident that all three of my intervals contain whatever parameter it is that I'm trying to find. So this is a troubling trend. As I add more and more confidence intervals, my overall confidence that all of these are correct is going down. And let's take it to a little bit of an extreme. Let's say I calculate 10 95% confidence intervals. Well, in that case, I'll do 0.95 times itself 10 times, which is 0.95 to the 10th power. And this is where we're really starting to see the problem. If I give someone 10 95% confidence intervals, I'm 95% confident in each individual one, but I'm only 60% confident that all 10 of them work. And so if I'm trying to create this sort of overall story about what I've learned and what I've seen, I'm actually not very sure that my complete story is correct. Only about 60% sure. And so this is going to lead to some problems. If I'm going to calculate more than one 95% confidence interval, I'm not 95% confident that all of them contain the parameter of interest. The good thing is, we actually have a couple different ways that we can solve this problem. So let's look at our first example here on the next page. If I'm going to make 4 confidence intervals, and I want to be 95% confident overall, 95% confident that all of them contain the parameter of interest, I'm just going to look at this sort of equation here, and I'm going to make this side be 0.95, and then I'll try to figure out how big the individual intervals should be to match up with that. All right, so I'm going to take my individual level of confidence, I'll raise it to the power of however many confidence intervals I'm calculating, and I'll set that equal to whatever I want for my overall confidence. So let me show you an example. I'm going to calculate 4 intervals. I want to be 95% confident. Well, I'll set 0.95 equal to 1 minus alpha star, and alpha star is just some sort of new significance level that I'm going to calculate. And I'll raise that to the 4th power. Because I want to know what 1 minus alpha star is, I can take both sides to the 1/4 power. That leaves me with just 1 minus alpha star here, times 0.95 to the 1/4. If you calculate that out, you'll get 0.98726, which tells me that my individual intervals should be 98.726% intervals. And if I wanted to figure out what significance level that is, I'll just take 1 minus this number, and this would be something that I could say to SAS, for example. Alpha equals 0.01274, and SAS would give me a 98.726% interval. We'll see that we can actually have SAS do some of this for us, but that's the general idea. So we can check our work. If you take 0.98726 to the 4th power, you'll see that you actually do get 0.95. And so as a reminder, if I want to be 95% confident that all 4 of my confidence intervals contain the parameter of interest, I'm going to make 4 98.726% intervals. I've solved the problem that I was running into on the previous page. If I make 4 95% intervals, my overall confidence is too low, so I'm going to bump up the confidence level for my individual intervals until I can get that 95% overall confidence that I really want. There's another example right below this. I would recommend pausing the video and trying it on your own if you're going through the notes right now. For this example, we want to figure out what level of confidence we need if we want to be 90% confident overall, and we're making 12 intervals. So you can repeat these steps that we just did and see if you can get an answer. I'm going to go through it right now as well, so hopefully you did pause to try this on your own, but we're going to go through the same steps. I'm going to take 0.9, what confidence I want, set it equal to my individual confidence levels to the 12th power. And then I'll do both sides to the 1/12th power. When I calculate out this side, I get 0.99126 equals 1 minus alpha star. And this is telling me that if I want to be 90% confident that all 12 of my confidence intervals contain my parameter of interest, I need to make 12 99.126% confidence intervals. In the next part of this set of notes, we're going to see that there's actually a shortcut method that we can use so we don't have to rearrange this equation every time. And then we're going to work back through the serial example that we've been talking about to see how we could use this idea to learn what differences there are in the population means and how big those differences are.